Okay, hey folks, last video in this module, we're gonna kind of start to begin our journey into spectroscopy by looking at the selection rules of simple atoms. I'm not gonna spend too much time with this, but as we'll see, those selection rules are gonna manifest in what we observe in reality. So, and we're gonna use the term symbols to help us understand that. So here's setting up the basis for a spectroscopic transition. So we recognize that our initial state will have some set of quantum numbers given by N, L, and ML, or really giving us a term, a main term symbol. And then our final state will have some different set of quantum numbers. And in the case of F, being less than I. So in the case of an initial state being higher energy than a final state, then light will be emitted in this process. If it's the other way around, if the initial state was less energy than the final state, then we'd have to pump light in to that system to make it go. So energy must be conserved in a spectroscopic transition. So the change in energy of the electron must be compensated by an emitted or absorbed photon. So this is stuff that we've kind of talked about in a lot of our other chemistry classes. What's less familiar to us is this total angular momentum. So angular momentum must also be conserved in a spectroscopic transition. And the way that this is achieved is from the spin change of the photon and the electron. So the change in angular momentum must be compensated by the electron for the angular momentum removed by the photon. So we're going to see that gives us a certain requirement in our terms that are allowed. So photons don't have any mass. However, it was shown by Dirac that photons can be described with intrinsic spin number 1. So we just talked about fermions being quantum objects with spin equal to 1/2. Photons are quantum particles with spin number equal to 1. Okay, so let's talk about this conservation of angular momentum, because this is lesser known and described from your previous classes. So for example, let's suppose we want to go from L equals 2 state to an L equals 0 state. So that would be like a d orbital going to an s orbital, for example. So we can describe the angular momentum of the electron with the following: L times L plus 1 h bar. We can describe this change, or the magnitude, I should say, of the angular momentum of the photon with S times S plus 1 h bar. So for the L equals 2 electron, that's going to have overall magnitude of root 6 h bar. So from 2 plus 1 is 3 times 2 gives me 6. When it goes to the L equals 0 state, it's going to have 0 angular momentum on the z-axis, right? But now there's this removed photon that carries away angular momentum with it. And the angular momentum of that photon will always be root 2 h bar, right? S equals 1 for photons. So 1 plus 1 is 2 times 1 is 2. So when this leaves the molecule, it is removing that root 2 h bar. So these things are not equal to each other. So this is a forbidden transition. In the case of a simple atom, we can't go from a d orbital to an s orbital. But what about a p orbital to an s orbital? Well, the L equals 1 state will have root 2 h bar angular momentum. When it goes to L 0, it will be 0, but it will carry away with it root 2 h bar angular momentum. So these two things are equal, thus going from a p orbital to an s orbital is allowed. And so this is just one simple example with delta L's. If we were to also put in this case with delta ml, we would also see another condition arise where ml can only change by either 0 or plus or minus 1 at a time. So we can't change ml by 2 whole numbers at a time. So with all of that together, we're going to see, right, the combination of these gives us the set of term symbols for hydrogenic atoms only. So this would be for hydrogen or for things that contain, one single valence electron. So here is another view at our hydrogen spectrum, which we've looked at before. And what I want to point out here now, you can see for hydrogen, right? Recall we said that, all of the shells are degenerate, right? Oh, I wrote S, but that should just be, that's my 1s level, and that would be 1s. This would be 2s, this would be 3s, and so forth, right? But we recall we said 2s and 2p are degenerate, or 3s, 3p, 3d are degenerate. But you notice now that transitions involving those levels are changing L by plus or minus 1. And specifically, if we looked at which exact position in the P block or D block they correspond to, it can only be a change in ML of 0 or plus or minus 1. So that's where we see, like in the case of these Balmer lines, they are all going from p orbitals to s orbitals. They're not going from s orbitals to s orbitals or d orbitals to s orbitals. They are specifically going from p orbitals to s orbitals. And that is confirmed with their angular momentum, okay? So there's ways that we can confirm that using magnetic fields and looking at the splitting of the levels in a magnetic field. So we're not going to get into too much detail of that. So I want to just move on past that. So just like we talked about in IR spectroscopy, there has to be a transient dipole moment oscillating at the same frequency of the electromagnetic radiation to have a spectrum. So we remember light is an oscillating electromagnetic field. When an electron moves from one orbital to another, it may induce a charge moving at a distance. So it might not have a permanent dipole moment standing, but it may possess a transient dipole moment as the electron moves from one orbital to the next. And just like we saw in IR spectroscopy, if the expectation value gives us a 0 value, there's no spectrum, or in other words, we violated one of our selection rules. If we get a non-zero value for the expectation value of the dipole moment operator, then we get a spectrum, and that spectrum, the intensity is generally proportional to the value of that dipole moment operator. I should also note that these dipole moment operators have much larger values than they did for vibrations. So for example, if we look at the value of mu z for a 2pz to a 2s, so that would become, negative ER cosine theta for the EZ. And then, this would be for hydrogen, right? So if we look at the dipole moment of going from 2pz to 2ps, it's a really large value. It ends up being negative 3e times the Bohr radius over the charge. That is about 7.7 dBi. So much, much larger than dipole moments we saw in IR spectroscopy. And this makes good sense because we're fully removing an electron from one position and putting it into another. So we can also begin to think about how this angular momentum business plays out when we consider that a transient dipole moment must be created, which is a charge over a distance. So if we look at this 1s to 1s transition, at first it appears like, oh, that should be giving us some new dipole moment. But remember, because it's symmetrical, all of those resulting vectors, whatever direction we draw them in, will all cancel out. So we get no transient dipole moment from this 1s to 2s, but we will get this transient dipole moment from 2s to 2p because there is a change in shape and overall charge distribution resulting in a transient dipole moment. So we can also then use this to understand spectra of somewhat more complicated atoms. And by more complicated atoms, here's a look at helium. So this is the helium spectrum. And now this is where it becomes useful to apply our selection rules as term symbols. So for the more complex atoms, delta S must be equal to 0. So what this means is multiplicity must be conserved in a transition. So we can only go from singlet to singlet or triplet to triplet. So for example, if I think about the helium ground state, 1s2. Here's my electrons. We know they're paired up. So we're going to look at two possibilities here. Suppose in one possibility, we promote an electron. So I'll show that by, promoting up to some upper level where they're now spin parallel. Or we can imagine a possibility, let's draw that again, where now they are anti-parallel. Well, hopefully we can recognize here that even though they're separated by different states, this situation is going to be a triplet, and this situation is going to be a singlet, and both are possible. We should remember from Hund's rules that the triplet state will be lower in energy than the singlet state. But now what we can also see from our term symbols is transitions from triplet to singlet and singlet to triplet are not possible. So our ground state here for helium was 1s0, right? So we can see now transitions to upper lying singlet states from the ground state are possible. But transitions from upper lying triplet states back down to the ground state are not possible. Those are forbidden. Applying the term symbols to our selection rules, we would also see that delta L can be 0 or plus or minus 1. So that's the main term. So you can see that we could go from P to S and D to P. Technically, we could get the same term. I could go to S, but only if L changes by plus or minus 1. And in the case of helium, that's not possible. So more complicated atoms, we might observe an S to S or P to P transition as long as delta L remains to be plus or minus 1. So similarly for J, we also get a set of terms that must be followed. Delta J can be 0, so we can go from a 3/2 to a 3/2, or a 1/2 to a 1/2, or plus or minus 1, so we could go from a J 3/2 to a J 1/2. We can't go from a J 5/2 to a J 1/2, right? And now this notation here, this symbol means forbidden. So what that means is we can have a delta J equals 0, right? I could go from a 3/2 to a 3/2, but I can't go from a J equals 0 to a J equals 0, right? Think about that. So delta J can be 0, but the exception within that is I can't go from J equals 0 to J equals 0. Okay, so now that was a lot. The videos were a little bit lengthy this week, so I appreciate you all staying up with the content, and we'll have lots of fun going through all these examples in class. I will see you all later.